Hi, my name is Chung Wong, and I'm going to present my final project for class CS224W. It's titled Characterizing and Predicting the Economic Network of Corporations. In this project, we set ourselves the task of predicting the correlation of stock price returns between corporations using the structure of the supply network. The project was divided into three parts. 1. Analyzing the supply network of US corporations using network techniques, for example, page rank, node-to-vec, etc. 2. Generating features from the network analysis to train a rigid regression model to predict correlations. And thirdly, we show that node-to-vec embeddings have the best relative performance in this task and shows promise for future research. So why did I choose this task? Well, for one, I think that the interlinkage of corporations within the supply network is a very interesting dataset to investigate. Looking on the left-hand side of the slide, we see a classic depiction of a linear supply chain with more raw materials going to a supplier, which then goes to a manufacturer, and so on, all the way to a customer. However, on the right, we see something which is a lot more realistic. It is the EgoNet of Intel Corp. And here we see that the relationship between corporations is much less linear, it's a lot more complex and interesting. Since around the year 2000, research in supply chain management has started using network analysis tools to look at the topology of the supply networks. At the same time, in finance, some research has been done on direct customer and supplier relationship and whether that has any effect on the stock prices of those two firms. In this project, we want to bring both threads together, i.e. look at a whole supply network and see whether the structure of the supply network can be used to infer anything about the stock prices of all the firms within that network. We think this is worthwhile to do as both the supply networks and stock prices are important aspects of the economy. The first thing to note about the data collection process is that the customer to supplier data is usually incomplete, i.e. we will not be able to find a complete database of every customer to supplier relationship because most firms regard those relationships as trade secrets. In our case, Bloomberg is the main source of data because it aggregates data from regulation SK disclosures, conference calls, capital market presentations, etc. And we also only consider firms which are members of the Russell 3000 index. This is the index of the 3,000 or so largest companies in the US and represents about 98% of the total investable stock market in the US. The supply network that we end up with has 3,007 nodes, where each node represents a single corporation, and 4,791 directed edges, where each edge represents a supplier-to-customer relationship. As you can see on the graph on the right, the degree distribution of nodes approximately follows a power law for up to a certain node degree, and the exponent for the power law is 1.15. One of the network analysis techniques that we used is PageRank. We see on the left that the nodes with the top PageRank scores are all large and complex corporations such as Walmart, Boeing, etc. It seems intuitive that such large firms would have an outsized effect on other firms within the supply network. Hence, we used each node's PageRank number as a feature for the training. Next, we looked at the supply network through the lens of motifs. First, we counted the frequency of non-isomorphic directed 3 subgraphs in our supply network. Then we compared that to a null model, in this case, a configuration model where random pairs of edges have switched endpoints. The graph on the right shows the set score for different types of motifs. The spike at 3 shows that the supply network has an over-representation of a particular motif, in this case 2 suppliers linking to a single customer with no other edges. shown in the graphic on the left. We then ran the motif-based spectral clustering algorithm on the supply network using a range of different 3 subgraphs as target motifs. We found that despite overrepresentation of the M10 motif in the network, none of the sweep profiles seemed to cluster the network convincingly compared to the others. We can see this on the plot on the left. The plot on the right of the Fiddler vector plots showed the same message. However, we still tested the effectiveness of this measure by using the clustering information as a feature to train our prediction algorithm. Finally, we generated node-to-vec embeddings for every node in the supply network. We then used k-means on those embeddings to cluster the nodes into different communities. The plots below show that this task is done well, and that the embeddings represent the nodes well, as each of the communities make intuitive sense. Different P and Q values do not have a big effect on the clusterings, and we use the entire node-to-vec embeddings for each node as a feature in the prediction model. To measure the performance of the ridge regression models generated by the different features, we use the R-squared score. R-squared of 0 implies the same as a constant model, i.e. the model outputs the same number regardless of the input. R-squared of 1 implies perfect accuracy. You can see from the table on the right that page rank and motif-based cluster features do not add any value to the model. However, node-to-vec is more promising, with statistically significant performance of around 0.55 R-squared. The table at the bottom shows that for different hyperparameters used for node-to-vec, the performance R-squared is relatively consistent. To conclude, I think the network analysis techniques that we used generated interesting results on the supply network. The node-to-vec representation of the nodes showed greatest promise for future work in terms of linking the supply network to stock prices. And finally, future work can be expanded to foreign companies given global supply chain. The evolution of the supply networks can be investigated over time, plus other avenues of future work. Thanks very much.